Hi, this is a video about compiler design, COM 642 and 6421. This video, I'm going to describe assignment number 1, which is lexical analysis. So first of all, let me share the screen. And if we go to Moodle, so this is week 2, and then the handout is here. You will also find the handout on my webpage. So if you go to the webpage here, click here, and you will also find the handout here, right? But let's stick with the Moodle page. So handout here. So you will see that, well, first of all, it links to my webpage. Here, and the webpage actually maintains a list of the changes that I may have made to every of the file that I'm sharing with you. So if you click again to this link and you see more entries in this table here, that would actually mean that there's new versions that have been created. I will try to avoid that, but sometimes there are some changes that need to be made. If there are, then they will be all listed here, and you would basically select the first one that's going to be on the top, which is the latest version. So at this point, there's only one. Let's hope that it's going to be this way for the rest of the semester. So this is a zip file. So a zip file actually contains a PDF that describes the assignment itself. And then it also gives you a list of files that, for example, input files that I'm giving you for testing, limited testing. As I said in the presentation of the project in the first week, testing is a major issue in compilers. It's a difficult issue. And you are responsible to test your own compiler, to provide your own test cases. I am providing you with some test cases, but in no way can you expect that these are complete test cases. I'm giving you examples, essentially. Okay. So that's a good starting point. It's actually a very good starting point, but there are many other cases that either are positive cases or negative cases. Of course, there are so many different possible positive and negative cases. That's the difficulty in testing a compiler. And you are responsible to provide your own test cases for each assignment. In this particular one, I'm giving you what I consider pretty much is a complete testing. So let's start with the assignment handout. It's bigger. Okay, so first of all, this is about the lexical analyzer. So what's a lexical analyzer? It's essentially your program is stored in a text file. So essentially you read the text file as a stream of characters. And then the job of your lexical analyzer is to scan this stream of characters and then generate a stream of tokens out of the stream of characters. In fact, your lexical analyzer component should not extract all the tokens. It should extract only the next token, because when you design the syntax analyzer or the parser, the parser will actually ask your lexical analyzer to provide the next token. So that's why your implementation of the lexical analyzer, what it should do, well, it first should connect itself to the file, but then when you call next token, function name next token, then it provides you with the next token that is extracted from the file. Of course, when you submit the assignment, you have to submit a driver that's going to repeatedly call next token, thus extracting all the tokens. But the function that's going to be used by the parser, which is the important part, is going to extract only the next token. Okay. So that's what should be your lexical analyzer. You see, it's pretty simple conceptually, but implementing it is, well, it is possibly, it is actually the most simple assignment of all the 5 assignments, but it's not to say that this is a simplistic assignment. So first of all, deadline, this is due on January 29th. There is a little possibility of extending the assignment. So don't expect that there's going to be extensions given to the assignment, okay? As a rule, I'm actually applying late submission penalties. Okay? So don't assume there's going to be extensions, and there is penalties associated with submitting your assignment late. Now, okay, so what is it that your lexical analyzer must do? Well, first of all, it must extract tokens. So in order to extract tokens, then what you must know is what is the definition of these tokens? What is the subsequence of characters that you extract from the file that constitute one token? So for every of the different kinds of tokens that you will extract, there needs to be a definition. That's what I'm providing to you here. So for example, each of the identifier, integer, and float are described here as somehow as a, you might say, a regular expression or a mini grammar. So essentially, this is the definition of identifier, which is a letter followed by any number of alphanumeric characters. That's the definition of alphanum, and then letter is defined here. Right? Alphanum is either a letter or a digit or underscore. So it must start with a letter and then can be followed by any number of letter, digit, or underscore. That's the definition of an identifier. So for those of you who use regular expressions, then you can see clearly that you could implement that using regular expressions. You will be allowed, you are allowed to use whatever you want to actually do this tokenizer or this lexical analyzer. If you use libraries, for example, Java has a tokenizer class, which allows you to do some of what is asked there. Particularity, though, of tokenizer classes is that they have their own limitations. So you should look carefully. If you use a tokenizer, you should look carefully as to whether it can do what I'm asking you to do. It's possible that you can't. And if you use a tokenizer that is not adapted to what I'm asking you to do, and you still choose to use it, and there are some tokens that you can't recognize, as I will show in the examples, then you will lose marks. Okay. So if you want to use a tokenizer class predefined, and make sure that you test it to make sure that it actually does what it's supposed to do, what I'm asking you to do. Here is a definition of integer, and here's the definition of float. Integer and float are the two only values that we're allowed to use in this programming language. So you don't have strings or any other kind of basic type. We're only manipulating numbers, essentially. And that's the definition of what is an integer, and that's the definition of what is a float. I'll let you read this. You will see that it's not trivial, let's put it this way, especially for float. Not very complicated, but it's not trivial. Then, so that's it for the more complicated things that require a definition. But there is also other tokens, such as operators, punctuation, and reserved words that are all listed here. Okay. So here, it's not telling you what is the meaning of these or how are they organized to form programs. It's just giving you the list of reserved word operators and punctuation. Okay. So that's not the job of the lexical analyzer to figure out if the tokens are organized in the right order to form a valid program, which would be what the parser will do in the second assignment. Then there is also possibility to have in the programs comments. So comments, you can have block comments that start with /* and end with */. And then inline comments that start with // and end with the end of line. So very common kind of notation in many programming languages. The comments have to be also identified as a token. Of course, these kinds of tokens are not part of the meaning of the program, but what's going to happen is that your lexical analyzer is going to identify them as a token. And then when the parser will receive such a token, a comment token, and it will just discard it because it has no meaning in the program. Okay. So you're not just skipping over the tokens, the comments, you are producing a comment token. Okay, so what is it that you have to do? First of all, for each assignment, I'm asking you to produce a document. Don't worry too much about, sometimes profs are asking very lengthy and detailed documents. Here I'm asking a document basically only for grading purposes. Okay. So it doesn't have to be very pretty, doesn't have to be very long. That's not the expectation. Okay. You're not going to be graded on the appearance of your document. I'm not expecting 50-page documents. No, I'm just asking very minimal information. Essentially, that's for information. You have to provide information. Things like this, your lexical specification. Here, I'm providing you a lexical specification. It is possible, as I told you before, it is possible that if you're using for example, the Java tokenizer, it is possible that you'll not be able to do, for example, the floating point numbers in exactly the same way as I specified in the assignment. There is a difference between your specification for a floating point number and the one that I provide. You have to provide your own lexical specification. Okay. Whatever you do, whether it's the one I provide or one that you changed, you need to provide your own lexical specification. By the way, as I said before, if you change the lexical specification, you will lose marks, but you have to provide it anyway. Section 2, a finite state automaton. As we will see in lecture number 1, you can, or if you would, any lexical analyzer that you design should, if you do it correctly or systematically, should follow some kind of automaton. An automaton that's basically specifying what happens when you read a certain character, you go to a certain state, and then you follow a certain branch, as I will explain in the first lecture about lexical analysis. So you read a character, depending on what character it is, you go in a certain branch in a DFA, and when you follow this branch and you reach a final state in this DFA, you have identified a certain token. Okay. So for every token that there exists, there would be a branch, a separate branch in this DFA that defines how you actually identify each of the tokens. What I'm asking you to do, to provide, is to provide this finite state automaton. I'm explaining in class the theory as to how you can actually, for example, take a regular expression and then translate it into a finite state automaton. There are some online tools that you can find that allow you to automatically generate a finite state automaton out of a regular expression defining your lexical specifications. I strongly suggest that you use such a tool to provide your finite state automaton. Some of you might be tempted to start doing the implementation without having the DFA, I would advise against it. Okay. It is, especially if you hard code your lexical analyzer, as I will show in class. I strongly suggest that you have the DFA before you start the coding. Okay. It's easy to think that you understand everything about what the lexical analyzer should do and all the different cases and so on. But if you have a DFA, and then as you code, you look at the DFA, it is going to minimize the possibility that you go in a wrong direction. Okay. So yes, provide a DFA that corresponds to your lexical specifications. Then I need you to provide me some kind of diagram or small explanation, reasonable explanation as to how your lexical analyzer is organized. Use of tools. So very simple paragraph describing what are the tools that you use for the implementation. For example, I'm asking you to do a DFA. I told you there are tools online. What is this tool that you use? If you use, for example, a Java tokenizer to do the implementation, what is this tokenizer? Any tool or library that you use, I want you to list it there and explain to me what you did with this tool. Then, of course, implementation, which is the main part of the of this assignment. First of all, it should be you have to implement a lexical analyzer. You also have to provide test cases and to provide some kind of driver. So the lexical analyzer should be able to recognize all the tokens that are mentioned above, that I explained before on the previous page. It should be a function that returns a token data structure containing the information about the next token identified in the source program file. So it reads from a file, reads characters, and then it produces something of type token. I will explain that in class, what should be this data structure. Token data structure should contain information such as the token type of this token, the lexeme of the token, as we will explain in class, and the location where you found this token in the source code. This is very important because anytime you will do, for example, error reporting, when you do syntax analysis, you will need to know where this token was found in the source file so that you can report errors according to, for example, the line number where this token was found in the source file. When lexical errors are found, an error token should be produced whose type is of a specific error type. Yes, so I'm providing you also, yes, that leads me to talk about what is it that you also have, which is here. So this is the zip file, so this is the PDF, and I'm providing you with some, for example, lex negative grading and lex positive grading. So my files, the source files that I'm providing you, that are programs essentially in this language that we are compiling, these are SRC files. So for example, if we go, let's take one of the examples. So we go here. So that's an example that I written in this language. So you see you have a function. This is a bubble sort implementation. You have a function bubble sort, takes parameters, returns void, has local variables, has two while loops, and if, and so on. It uses arrays and so on. And then you have a print array that's going to print to the console or the screen. And then you have the main function. Okay. So this is the kind of program that we will be able to compile eventually. If you take this program and you feed it to your lexical analyzer, it should be able to tokenize this file. Okay. More specifically, I also gave another example here, but more specifically, provided you with some specific examples. For example, positive grading, this one here. This is essentially the list of all the keywords as exactly as there is in the assignment handout. And also here, there are some integer numbers. Here, there is floating point numbers. Here are some identifiers, and here are some comments. Okay, so these are all positive cases. So you should be able to positively identify every token that is in this file that is making you exercise the identification of all possible kinds of tokens in this language. Okay, these are all positive cases. As you may see here, there is one of the things I'm asking you, as we will come back later in the PDF, in the assignment description, you should create a file called out_lex tokens, which is essentially outputting all the tokens that you found, or a text representation of the tokens are written inside of this file. So let's look at this one here. So for example, this is a token equal that you have identified, and then plus, and then or, and then open parenthesis. So basically here, this is the token type, and this is the lexeme. The lexeme is the sequence of character that you have identified as, that you have mapped as being, in this case, an open par token. And then the third thing here is the line at which you found this token. Okay. So of course, here this corresponds to my lex positive grading file that I have shown you a few seconds before. So essentially, when you tokenize, when you call your tokenizer, your lexical analyzer to read the lex positive grading.src file, it should, well, extract all the tokens and also output them to this out_lex tokens file. You should also output or create a file called out_lex errors. If you find some errors, then they would actually be output to this file. In this positive case, there's no errors, so this file should be created and be empty. Then I provide you with some negative cases. So these are, for example, these are invalid characters. So this is one of the lexical errors that you should have. If you're reading a character that is not in the character set allowable for this language, then you should actually output a lexical error in the lexical errors file. Same thing here. If you look carefully, I will not go here into the details of why these all are negative cases, but these, according to the lexical definition that I provided to you, these are all negative cases. For example, it may seem that these are integers, they are not. For example, they all have a leading 0, which all makes them invalid number. For all different kinds of reasons, these are also invalid floating point numbers. So are these here. And these are some cases of invalid identifiers. Okay. So, okay, so let's go to lex errors for this one. So this is an example here of error messages that you should output in the out_lex errors file for this file that I've just shown you. One of the things which I will explain in class, I'm not going to explain that here, but when you read the actual lexical specification, there's actually different ways you can actually interpret what's the outcome that's going to result if something is not following the lexical specification. So there's two alternatives for some of the cases, especially for identifiers and for numbers. So depending on how you interpret things, you may have alternate interpretations, essentially, of the lexical specifications. Here I'm providing you with two different interpretations, two different alternate possible interpretations here in these two different cases. Okay, so let's go back to this. So, okay, so a lexical analyzer should output the tokens in the file. And this file should be named the same name as the original file, .outlex tokens. Okay. This is essentially a file that stores the token stream. Now, why I'm asking you to output things in a file, two things. First, for grading purposes, to see that you're identifying the right things, to have a trace of what you did, of what your lexical analyzer did. Plus, it is also going to be useful for you for debugging later on, as, for example, you will do your parser. Maybe you want to see what are the tokens. For example, let's say your parser failed. You want to see up to where the parser actually parsed the program. So it's a tool that it is a feature that's helpful to you. That's how I see it. That's why I'm asking you to do this. One, for grading. Second, to help you in the development, to have a trace of things being produced or analyzed. And then, as we just saw, you should also output a outlex errors file. So same name as the original file, except that the extension is different, should be outlex errors. Test cases, as I shown you, I'm providing you with some files, example files. For assignment number one, it's reasonable to expect that what I'm providing to you is sufficient. Okay? But starting assignment number two, we will see that it's not that evident to actually completely test the compiler. So you must provide your test cases in your assignment submission. Then you must provide a driver, well, because the program that I'm asking you to produce is essentially a function, for example, called next token, that extracts only the one next token from the file. So if you want to test that and run it, then you should have a driver that will repeatedly call this next token function to actually extract everything from the file. So you should have a driver that allows the marker or you in the demonstration to extract all the tokens. Okay? Even though your program, the useful part of your program is the next token function that extracts only one token. Okay. So I'm going to talk a little bit here about what I meant here by different interpretations of the lexical specification. So let's say we have this here. So let's take this case here, 012.340. So you might say, well, this is a floating point number, 12.34, right? So that might be a reasonable interpretation or expectation. But the fact of the matter is that this is not what the assignment, the specification for a floating point actually says. If you look here, a floating point starts with an integer. An integer starts with non-zero. So that actually means that a floating point number cannot start with zero. By the same reasoning, also, for example, you have also non-zero here. So basically what I just said before means that an integer cannot have what is called leading zeros. 0, 1 is not number 1. It's an invalid number. Okay. Same reasoning applies to the fraction part of a float. So for example, fraction says dot any number of digits followed by non-zero. So that means here that the fraction part of a float cannot have trailing zeros unless it is dot zero. Okay. So basically, numbers, you cannot have leading zeros or trailing zeros. So that's why this number here is an invalid number. Or let's take this one here. Well, this one is an invalid number because it has leading zero here. This was an invalid number because it has leading zero. This was invalid because it has a trailing zero. So, okay. So, but, however, you have two different ways of thinking here. So it's either this is 12.340, it's an invalid number. Or this is 12.34, which is a valid number, which is a token float, as I'm saying here. So you have identified here float 12.34. And then as you identify this substream of characters here as a float, then you go and identify the next token, which is 0. So here you have, by still following the description, the definition that I gave in the first page, you have two interpretations. Either you say this is an invalid number because it has a trailing 0, or you say this is a valid float and this is a valid int or integer. Okay, so that's why there's two different interpretations. Neither of these two interpretations are violating the definition that is provided on the first page. Okay. So that's why I have these two, as I've shown here. That's why I have these two alternatives here. Alternative 1, alternative 2. Okay, so that's it about that. So you have to submit your assignments using the modal page. Please use the instructions that are provided here. Okay. This is here the grading scheme. So you need to so there's some analysis part which is related to what you're going to provide in the document. There's a design part. Again, you must provide your design in the document. Of course, part of your design and implementation is whether the program does what it's actually supposed to do according to the assignment statement, which is, of course, a very large part of the entire grade of the assignment, right? You must do error reporting. That's another part of the assignment. Output the token stream, error recovery. Error recovery means that if you find an error, that you're able to continue the tokenizing of the program. You should not stop because you found an error. We will see that in the how to do error recovery in class. Test cases, so you should have reasonably complete test cases. For assignment number 1, it is sufficient, I might say, to use the examples that I gave you in the zip file. And then use of tools is basically to describe what are the tools that you use and how you selected them. So that's it for that. So that's it for this video. Thank you. Bye-bye.